Hello everyone. So in the last lecture we talked about viscoelasticity of polymeric materials, where we saw that the viscoelastic response typically is a kind of response which is intermediate to that of a purely elastic response and a purely viscous response. So we also discussed a couple of simple mechanical models to describe such viscoelastic behavior. In today's lecture we will carry forward that discussion on viscoelasticity, and we will specifically talk about a couple of other parameters which are useful in studying the deformation behavior of viscoelastic materials and the corresponding mechanical response. We will also talk about the dynamic mechanical analysis, where the response to an oscillating load is studied. So, the response of a viscoelastic material to let us say sinusoidally oscillating load, that is what this dynamic mechanical analysis aims to study. So, we will briefly look at that topic, and towards the end we will again briefly discuss the rheology of polymeric liquids such as polymer solutions and melts. So, regarding the content of today's lecture, we will start with discussing a couple of parameters related to the viscoelastic response. So, first will be the creep compliance, and the next will be the stress relaxation modulus. We will define these parameters. We will also talk about what is called the Boltzmann superposition principle, which applies for linear viscoelastic materials and which allows one to obtain the state of stress or strain in a material at a given time if the entire deformation history for that material is known, and provided the material is linear viscoelastic. After that we will focus on dynamic mechanical analysis, whereas as we discussed we will talk about how the viscoelastic materials respond to oscillating kind of load. Then towards the end we will focus on rheology and flow behavior of polymeric liquids. So, here we will see that in many cases the flow cannot be described using a Newtonian kind of model. So, non-Newtonian flow behavior of polymeric liquids will be studied, and some simple models that describe such non-Newtonian behavior that will also be explored. And towards the very end we will briefly look at the dependence of the quantity viscosity on temperature as well as molar mass of the polymer. So, to begin with we will start with the quantity creep compliance. So, creep compliance is a parameter which allows the strain in a material at any given time to be determined, provided the material is subjected to some stress or some load, and it is a function of time. So, creep compliance directly relates the strain developed to the stress applied, and the relationship is simply linear and looks like this. So, epsilon, which is a strain induced, will be equal to the creep compliance times the stress applied. So, now if we try and see how one of the models that we discussed in the previous lecture for linear viscoelasticity, how that model can be used to obtain an expression for creep compliance. So, we discussed in the last lecture that the creep behavior is modeled in a better way by the Kelvin-Voigt model. So, we will consider that model here. So, if we consider Kelvin-Voigt model, then the creep behavior is shown by this expression. Again, this is something that we discussed in the previous lecture, and the expression for strain upon application of some fixed stress sigma naught for Kelvin-Voigt model is given by this relation. So, now using the expression defining the creep compliance, we can obtain an expression for the creep compliance for a Kelvin-Voigt model. So, if we do that, this creep compliance is simply the strain developed by the applied constant stress. So, that is given by 1 over E, which is the elastic modulus, then 1 minus exponential of minus T by tau naught, where tau naught is the relaxation time. So, in this way we see that for if we have models of viscoelasticity available, we can obtain expressions for creep compliance from there. Now, creep compliance is a quantity or a parameter that relates the strain developed to the applied stress. In a similar way, if we apply stress, if we apply let us say strain to a material, a viscoelastic material, then what kind of stress is developed, that is given by another parameter which is called the stress relaxation modulus. So, that is what we will consider next. Okay, so, the stress relaxation modulus is given by this quantity GT, it is a function of time, and it allows the stress to be determined as a function of the applied strain. So, the relation between stress and strain as given by this stress relaxation modulus is again linear, and the stress at any point of time sigma t is related to the strain epsilon by this expression, where this stress relaxation modulus G t is the quantity that relates the stress developed to the strain applied. So, again like in the previous case, like in the case of creep compliance, we discussed the Kelvin-Voigt model and obtained an expression for creep compliance. For stress relaxation modulus also, let us consider a simple model that we discussed in the previous lecture and see how an expression for stress relaxation modulus can be obtained. So, in the previous lecture we had discussed that the stress relaxation behavior, where the stress is monitored as time under a given applied strain. So, that is described in a better way by the Maxwell model. The Kelvin-Voigt model is not able to capture the stress relaxation behavior of viscoelastic materials. So, the Maxwell model better captures that behavior. So, we will for the stress relaxation modulus, we will focus on the Maxwell model of viscoelasticity. So, if we have Maxwell model, then from the previous lecture again the expression for the stress as a function of time as developed for the Maxwell model is given here, and the constant applied strain is epsilon naught. So, again now if we go back to the expression that defines the stress relaxation modulus, then from here we can see that the G t is nothing but sigma by epsilon. So, if we do that, so sigma by this epsilon naught, which is a constant strain applied, that ratio is given by this expression E times exponential of minus t by tau naught, and that is the expression for stress relaxation modulus for a Maxwell model. So, these are couple of quantities of parameters that are important in the study of deformation and response of viscoelastic materials to applied load, whether it is applied stress or strain. Next what we will do is study principle known as a Boltzmann superposition principle, which allows one to obtain the stress or state of stress or the state of strain in the material as a function of its with a knowledge of its deformation history. So, if a material is deformed in several different steps over a long period of time, then that if the entire deformation history for the material is known, then the state of stress at a given point of time can be obtained using the Boltzmann superposition principle. So, the Boltzmann superposition principle as we discussed allows the determination of state of stress or strain in a linear viscoelastic material provided the deformation history is known. So, it must be stressed that this principle works only for linear viscoelasticity, and of course, if the viscoelastic behavior is non-linear, it is much more complex, and the simple models that we have been discussing they will not apply. So, for linear viscoelastic behavior, then this Boltzmann superposition principle can be applied. So, let us consider a case where stress is applied in multiple steps to a given sample of a material, and let us see how the strain varies with time, and how the Boltzmann superposition principle can be used to obtain the state of strain in the material at a given point of time with a continuous application of stress which might be changing with time. So, if we have stress that is varying during the deformation of a viscoelastic material, then what this Boltzmann superposition principle says is that the overall strain or the overall deformation in the material is just given by the linear sum of the individual strains that in the material that are induced in during the different steps of stresses applied. So, the overall deformation is given by the algebraic sum of strains during each loading step. So, what we are saying is that the stress is being changed step by step, and correspondingly strain will develop in the material, and it is a viscoelastic material. So, a kind of creep behavior will be shown for each stepwise application of stress or load. What is the state of strain or the amount of strain developed in the material at a given point of time, that we can obtain as an algebraic sum of all the strains or deformation in the material induced due to each of the loading steps up to that point. So, if we illustrate, try to illustrate this with a graphical kind of approach, then what we can say is that let us say we are plotting time on the x axis, and on the y axis if we are plotting stress first, then let us say initially for some time t equal to 0, initially there is no stress, and then at time t equal to some value tau 1, let us say a step stress of magnitude delta sigma 1 is applied, and then again at another time tau 2, another step stress of let us say magnitude delta sigma 2 is applied, and so on for different periods of time the load or the stress is being increased in a stepwise fashion. So, for this kind of a loading history, Boltzmann superposition principle allows us to calculate the strain at any given point of time as a linear or algebraic sum of all the strains produced by the individual loading steps together, and this is something that will allow for apply for a linear viscoelastic material. So, if we consider the strain at time t due to this first loading step, so this delta sigma 1 here. So, due to that the corresponding strain produced will be given by a relation that contains the creep compliance that we had just introduced in a couple of slides back, and that creep compliance multiplied by the amount of stress that is applied. So, that gives us a strain at any time t after this quantity tau 1 because this is the time at which this stress delta sigma 1 is applied. So, after at any time t after time tau 1, the strain due to this particular stress delta sigma 1 is given by this expression, and this creep compliance will have a value which will correspond to a time of t minus tau 1. Similarly, for this second load that we are applying delta sigma 2, the corresponding strain produced due only to that particular load will be given by again the creep compliance multiplied by the stress. Okay. So, in a similar fashion, if successively further loading is done, then for each loading step the corresponding stress multiplied by the creep compliance, that will give us the contribution of that part of the loading to the strain. So, the overall strain at any time t, what the Boltzmann superposition principle says is that it is the overall strain t at overall strain at any time t is given by algebraic sum of all the those individual strains produced by the different loading steps. So, this overall strain epsilon as a function of time is given just by the sum of epsilon 1, epsilon 2 and so on. So, if we substitute that, then this overall strain is given as a summation over the product of the creep compliance and the delta sigma corresponding to each loading step, and if we have n such loading steps, then the overall strain will be given by the sum of all the corresponding loading steps. So, this is a case if we have if the stress is being varied in a discrete fashion. So, stepwise we are changing the stress. If the stress is changing continuously, then instead of this summation the strain is described using a integral. So, for a continuous variation of stress, the strain as given by the Boltzmann superposition principle is this integral of again compliance times d sigma, and the lower limit is taken as minus infinity to consider all the entire possible deformation history that the material has gone through. And this stress that we have, if this stress is changing with time, then instead of writing in this way, the strain is more commonly written in a way where the integral is over time. So, that can be done by changing the d sigma to d sigma d tau and then integrating over this time. So, that is the expression that we obtain from the Boltzmann superposition principle if the stress is varying continuously or the loading of the material is being changed continuously. In a similar way, the Boltzmann superposition principle can also be applied to obtain the stress developed in a material if the strain is being changed in either in a stepwise fashion or continuously. So, next let us see how those expressions look like. So, if the strain now is varied during deformation of a viscoelastic material, then the state of stress can be determined using this Boltzmann superposition principle as again the linear combination or an algebraic sum of all the individual stresses produced due to the individual strains that are being applied. So, if each contribution is summed, and that gives the overall stress at any time t. So, the algebraic sum of stresses due to each loading step. So, if again for a first loading step strain delta epsilon 1 is there applied, then the corresponding stress will be sigma 1. Similarly, for the next loading step, if the strain is delta epsilon 2, then the corresponding stress is sigma 2, and we see that the applied strain and the produced stress, they are related by the stress relaxation modulus in this case now. So, the Boltzmann superposition principle again says that the overall stress at any time t is just given by the linear sum of all these individual stresses. So, that is what we do, and for again finite, discrete or stepwise change in the strain, we can just write the overall stress as a summation. That summation we can write like this, where again the stress relaxation modulus appears here. And again as in the previous case, if the deformation history is such that the strain is changing continuously, then instead of the summation, an integral can be used to describe the state of stress at any point of time t. That is given by again this integral, where it's the lower limit in time is from minus infinity to consider the entire possible deformation history again. And as before, if strain is changing with time, then the integral is better expressed as an integral over time, and that can be done by introducing this derivative d epsilon d tau, and then the variable over which integration is carried out is changed to this tau. So, these are the couple of ways in which Boltzmann superposition principle can be applied to obtain either the state of strain or the state of stress in a viscoelastic material, provided its entire deformation history is known to us. So, now what we will do is next we will consider the response of such viscoelastic materials to oscillating or let us say sinusoidally varying kind of load or deformation. Till now we have focused only on loads that are let us say varying linearly or let us say if they are constant. So, in a case where the variation of applied load is of an oscillating fashion, then we will see that some interesting kind of behavior is observed, and such kind of study forms the area of what is called dynamic mechanical analysis of such materials. Under dynamic mechanical analysis, we will focus on the behavior of a viscoelastic material that is subjected to an oscillating load, as we discussed. So, this oscillating load typically is represented as a sinusoidally varying stress or strain. Okay. So, in real applications of viscoelastic polymeric materials also, many times the material or the polymer will be subjected to a load that is changing with time in a kind of with a certain frequency. So, such kind of load is well replicated by this dynamic mechanical analysis, where a sinusoidally varying oscillating load is considered. So, the sinusoidally varying stress or strain is applied, and we measure the strain in these kind of experiments. If we consider a sinusoidally varying stress, then the stress sigma can be written simply as a constant sigma naught multiplied by sine of omega t, where this omega is called the angular frequency of variation of this stress, and angular frequency, the units are radian per second, and it is related to the normal the frequency f by just this relation omega equal to 2 pi f. Now, let us see that if this sinusoidal kind of oscillating load is applied, then what kind of response can we expect for different kind of materials. So, if we have a purely elastic material, then in that case the response that we get is that the strain developed also shows a sinusoidal kind of variation, and it oscillates with the same frequency as the stress. So, the strain frequency will also be omega, and it does not show any phase lag with respect to the stress applied. Okay. So, for a perfectly elastic solid, the strain will be in phase with the applied stress, and it will oscillate at the same frequency as the applied stress. Next, if we consider the response of a purely viscous material, a purely viscous response to this sinusoidally varying stress, then in that case we can consider the case of a simple Newtonian liquid. So, what is observed is that the strain actually lags behind the applied stress in the case of a purely viscous material, and the angle by which the strain or the phase angle by which the strain lags the stress is 90 degree or pi by 2 radian. But the strain again also oscillates with the same angular frequency as the applied stress. So, the omega is the same, but the strain is not in phase with the applied stress, it lags the applied stress by an angle pi by 2 radian. So, that is what we have mentioned here. And this is for a purely viscous response. Now, viscoelastic response, what we can expect is that it will typically lie in between these two extremes of purely elastic and purely viscous response. So, for viscoelastic materials, if a sinusoidal kind of load is applied, then the corresponding deformational strain that also varies sinusoidally at the same frequency as the applied load, but it lags the stress by some angle, but this angle typically is between 0 and 90 degree. So, a lag of 0 degree corresponds to a purely elastic response, a lag of 90 degree corresponds to pure viscous response, and for a viscoelastic material this lag or the phase angle by which the strain lags the stress, that is between this 0 and 90 degrees. So, the strain as we discussed lags by a phase angle delta for viscoelastic material. In general, what we can do is that for viscoelastic materials we can write the stress and strain variation in this way, where instead of showing the strain lagging by an angle delta, we have instead shown that the stress is leading by a phase angle delta. So, it is equivalent. So, if we consider a sinusoidal stress of this kind, then for a viscoelastic material the strain will be lagging, and we will have to write the strain as epsilon naught sine omega t minus delta. But instead of that, what we have done is written the stress as leading the strain by this phase angle delta, and both representations are equivalent. So, there is no issues. So, the strain is given by epsilon naught sine omega t, where again omega is the frequency, and for stress this delta is the phase angle, the phase difference between the strain and the stress. So, again if we consider these equations for the oscillating load and the corresponding strain produced in a viscoelastic material, then this sine omega t plus delta, that we can expand. So, if we expand this sine omega t plus delta, this is the expression that we get. This is a standard trigonometric expansion. Sine of a plus b is sine a cos b plus cos a sine b. So, that is what we have done here, and what we can do is now identify these two terms, the first term here as well as the second term here, as two components of the applied load or the applied stress. So, what we can say is that the first term that we have identified here, that is a component of the applied stress that is in phase with the strain developed. The phase difference between this component of the stress and the strain is 0. So, whereas if we consider the second component of this stress, then that component can be thought of as lagging. So, if we consider the second component, that component can be thought of as out of phase with the strain by an angle of 90 degrees. So, leading the strain by an angle of 90 degrees. So, this component is in phase with the strain, and this component of stress is out of phase with the strain by an angle of 90 degrees, and that we can say observe by identifying that cos of omega t is simply equal to sine of omega t plus 90 degrees. Okay, so, that is again a standard trigonometric identity. So, this second component where this cos of omega t is there, that we can write as sine of omega t plus 90. So, we see that now this component has this extra plus 90 degree, that extra phase angle compared to the strain that we have. So, this component leads the strain by an angle of 90 degrees, whereas this component of the stress is in phase with the strain. So, the component of stress sigma naught cos delta, that is what we have written here, that is in phase with the strain, whereas the second component sigma naught sin delta, that is out of phase with the strain by this angle pi by 2 radian. So, now these two components we can basically write in terms of certain moduli or dynamic moduli, and that is what we will define next. So, the dynamic modulus that is in phase with the strain now then can be defined as E1 is equal to this in phase component of stress divided by the amplitude of strain. So, sigma naught cos delta divided by, and this dynamic modulus that is in phase with the strain, that is called the storage modulus usually. Similarly, dynamic modulus that is in phase with or out of phase with the strain by an angle pi by 2 radian, that we can define as the second component of this stress by the amplitude of the strain. So, sigma naught sin delta by epsilon naught, and that is represented as E2, and that is usually referred to as the loss modulus. So, the in phase modulus is a storage modulus, and that corresponds to elastic response to the deformation, whereas the E2, which is the which we are referring as a loss modulus, that corresponds to a viscous or dissipative kind of response to the deformation applied. So, these two moduli we can express the overall stress again in terms of E1 and E2 in this way based on these two definitions, as well as this equation we can write sigma in terms of E1 and E2 like this. And also the ratio of E2 and E1, that if we take the ratio E2 and by E1, then that ratio will be equal to the tangent of the phase angle delta. So, that ratio is actually an important quantity and that is referred to as the loss tangent. So, this tan delta, which is just E2 by E1. So, if we divide this expression of E2 by the expression for E1, we will get tan delta. So, this ratio of loss modulus to storage modulus is tan delta, and this tan delta is referred to as the loss tangent. So, the two moduli that we have defined here, they usually in many cases are combined as a single complex moduli of this form, modulus of this form. So, where E star is a complex modulus, and even the storage modulus is expressed as the real part of this complex modulus, and the loss modulus E2 is represented as the imaginary part of this complex modulus E star. So, if we substitute the expression for E1 and E2, we get this expression for the complex modulus. So, till now we have discussed dynamic mechanical analysis considering the application of a certain kind of oscillatory stress. So, if we focus specifically on the application of oscillatory shear stress, so under oscillatory shear conditions, this expressions that we have developed till now, the same expressions will apply. Only thing is that instead of the strain that we are using, specifically the shear strain will appear, and instead the storage and loss moduli that we have discussed, they will be defined in a similar way, but their notations are typically different for studies under oscillatory shear. So, if you have oscillatory shear, then the stress again is the sinusoidal function leading the strain by an angle delta. And for strain, we will specifically look at the shear strain represented by gamma, and again stress can be expanded as done previously, and we can identify the in phase component and the out of phase component of the stress with respect to the strain. And the dynamic modulus that is in phase with the strain, which is the storage modulus, that is represented in the case of oscillatory shear by this symbol G prime usually. So, that is again defined as sigma naught cos delta by gamma naught, and the modulus that is out of phase or out of phase by pi by 2 radian from the strain, that is defined as sigma naught sin delta by gamma naught, and this is represented by G double prime typically, and this is the corresponding loss modulus. So, the tan delta again can be defined as the ratio of the loss modulus to storage modulus, and the overall stress also can be expressed in terms of the storage and loss modulus like this. So, the overall stress, if we just combine these two equations with this equation, we will get the overall stress in terms of G prime and G double prime. and tan delta, as we discussed, is just a ratio of loss and storage modulus, and this is the loss tangent tan delta. So, this is G double prime by G prime. And finally, the complex modulus in this case of oscillatory shear can also be defined as was done previously, and this complex modulus is just G prime plus I times G double prime, that is given by this expression. And we see that the moduli that we have, these are written as functions of omega, or the functions of the applied frequency. We see in these two equations that G prime G double prime as functions of delta, or the phase angle. So, it is observed that the phase angle actually is a function of the applied frequency. So, that is why moduli that we have, since they are functions of the phase angle, they are correspondingly also functions of the applied frequency. So, now that we have discussed the dynamic mechanical analysis of viscoelastic materials where an oscillatory load is applied and the response is studied, let us briefly discuss physical significance of some of these quantities. So, a measurement of these quantities like the storage or loss modulus as well as the loss tangent tan delta as a function of the applied frequency allows one to obtain information about the molecular motions that are taking place inside the polymeric sample that is being explored. So, if we have a purely amorphous material, then it is relatively more convenient to identify the different types of motion that are taking place with the behavior of these quantities, the tan delta as well as E1 and E2 with respect to changing frequency. If we have semi-crystalline material where crystalline fraction is also present, there the analysis becomes more complex. So, but for a general, let us say, amorphous polymeric material, what is observed is that corresponding to molecular motions taking place inside the polymeric material, the characteristic frequency of those molecular motions, if they correspond to the frequency at which the load is being applied, then quantities like tan delta show characteristic peaks. So, if we plot tan delta as a function of frequency, some peaks are usually observed. So, the large peak in tan delta corresponds to the glass transition in polymeric material where which marks the onset of significant molecular motion of polymer chains. Similarly, if we have a small range segmental motion of a few bonds, concerted motion of a few bonds of a polymer chain, or let us say motion of the side groups of a polymeric material, then such motions will also get reflected in the tan delta graph as some small maxima. And typically instead of studying the variation of this tan delta or E1 and E2 as a function of frequency, what is done is the variation is studied as a function of temperature. So, temperature can also be varied, and variation in temperature actually can produce similar effects as variation in frequency. And again there the temperature at which tan delta shows a maximum, that will correspond to the glass transition temperature. So, at glass transition temperature, which marks a significant onset of molecular motion, this tan delta shows a strong characteristic peak. Okay. So, what we see is that these quantities that are studied in dynamic mechanical analysis allows us to explore and study the molecular motion of the polymer chains and side groups. So, that is why this technique, dynamic mechanical analysis, is a powerful technique and useful for studying the characteristics of polymer molecular motions. So, next let us see if we consider such a sinusoidal kind of load and use a simple kind of viscoelasticity model that we had developed in the previous lecture. Let us try and see what kind of predictions are made or what kind of expressions that we obtain. So, if we consider the Maxwell model that we had developed in the previous lecture, there the rate of change of strain is related to the rate of change of stress as well as the stress by this expression. And if we introduce the quantity tau naught as eta by E, where tau naught is the relaxation time corresponding to this model, then we can write the Maxwell model the equation for this Maxwell model in this way. So, now let us see what happens if an oscillatory kind of load is imposed on this Maxwell model. So, if we consider epsilon as epsilon naught sin omega t, so an oscillatory kind of strain, and try to solve for this quantity sigma, that is the stress, using Maxwell model. So, we will get this ordinary differential equation again, and this equation is also a first order linear ordinary differential equation, which can easily be solved by the method of integrating factors. So, by applying that method and solving this equation, the expression for stress that we get looks something like this, and it contains these two terms, one having the sin omega t and the other having cos omega t terms present. So, now if we compare the expression that we obtained from the Maxwell solution of the Maxwell model to the expression for this oscillatory shear stress, which as discussed a couple of slides back is this. So, if we compare these two and try to relate the sin omega t term here with the sin omega t term here. So, we will see that this term we can say as being equal to this term here. Similarly, this term, which is the prefactor for the cos omega t, that we can say as being equal to this term here. So, using this kind of comparison, we can obtain expressions for E1 and E2, which are the storage and loss moduli. So, the storage modulus as predicted by the Maxwell model is given by this expression, loss modulus by this expression, and if we take the ratio E2 by E1, that gives the loss tangent tan delta, and in Maxwell model that tan delta is given by 1 over tau naught omega. If we now try to, let us say, plot these quantities E1, E2, which is the storage and loss moduli, or the tan delta as a function of omega, then what we will see is that E1 actually shows an increase with increasing omega, which is a reasonable representation of the behavior observed in actual viscoelastic materials. E2 actually shows a peak or a maximum at a certain tau omega value, tau naught omega value. So, at omega is equal to 1 by tau naught, at that condition or at that value of frequency, this E2 shows a peak. The fact that E2 versus omega plot shows a peak for this Maxwell model, that is also in line with experimental observations. However, if we see tan delta and if we plot it as a function of omega, we will see that tan delta continuously decreases as omega is increased, and that is something which is not very consistent with experimental findings, where tan delta is shown to exhibit a maximum, particularly at the corresponding to the glass transition. And so for some other transitions in molecular motions, also some other maximum values of tan delta or peaks in tan delta can be obtained. So, we see that the Maxwell model, although it captures the behavior of change in storage and loss moduli with omega to a reasonable extent, but it is not able to capture the behavior of tan delta with omega. Okay. So, that since the Maxwell model is a relatively simple model, we do not expect it to capture all the physical phenomena, and the tan delta behavior is not captured well. Instead, if we use the standard linear model and try to again solve the equation for an oscillatory kind of load, then the tan delta peak and other characteristics may be observed as well. So, this here was just a simple illustration of what happens when an oscillatory load is imposed on a simple model of polymer viscoelasticity. And with this discussion, we will conclude our discussion on viscoelasticity of polymeric materials and move on to briefly discuss the rheological and flow behavior of polymeric liquids, particularly polymer melts. So, if we consider polymeric liquids like polymer solutions or polymer melts, in general at reasonably large values of shear rates, these materials show what is called non-Newtonian behavior. So, to understand non-Newtonian behavior, let us just first recap what the Newtonian behavior looks like mathematically. So, Newtonian fluid is defined by a fluid where the shear stress tau, so here we are using tau for the shear stress. So, instead of tau we can also use sigma, we have been using sigma in general for the stress in our discussion. So, whether it is tau or sigma, it is equivalent. So, for a Newtonian fluid, that is proportional to the shear rate. So, this gamma is the shear strain, and if tau is the shear stress. So, here let us say we are representing the shear stress by tau, with the knowledge that previously we have used the symbol sigma for the shear stress as well. So, but in the discussion of flow behavior of liquids, typically shear stress is many times expressed as tau. So, that is what we will use here. So, it is proportional to, directly proportional to the shear rate or rate of change of shear strain with time, that is this quantity, and the proportionality constant is this quantity eta, which is referred to as the viscosity of the Newtonian liquid. Okay. So, we can write this tau or the shear stress as simply eta times gamma dot, where gamma dot is a time derivative of gamma, which is the shear strain. So, gamma dot is referred to as shear rate. So, for Newtonian liquid the viscosity or the quantity eta is a constant, it does not change with the shear rate. So, for many liquids non-Newtonian kind of behavior is observed where the viscosity actually changes with shear rate. So, an extension of this Newtonian kind of behavior is what is called the generalized Newtonian fluid behavior, where the relation between the shear stress and the shear rate is given by a form that is similar to the Newton's law of viscosity, but now the viscosity eta is allowed to be a function of the shear rate. So, for a generalized Newtonian fluid, the viscosity is a function of the shear rate, but the mathematical form of the relation between shear stress and shear rate that is identical to what we have for the Newton's law of viscosity. And this viscosity which is a function of shear rate, that is referred to as the apparent viscosity, and this kind of a model can capture the behavior of non-Newtonian many non-Newtonian fluids. So, for the case of polymeric fluids, let us say polymer melts, what is typically observed is that the behavior, non-Newtonian behavior that they exhibit is of the shear thinning kind. So, concentrated polymer solutions and melts typically show shear thinning behavior. In some cases, in rare cases, shear thickening behavior can also be observed for some polymeric liquids, but mostly shear thinning behavior is observed. So, we will focus on the shear thinning behavior. So, by shear thinning, what we mean is as the shear rate is increased, the viscosity of the material actually decreases. So, this decrease in viscosity with increase in shear rate, that is characteristic of a shear thinning fluid, and for a shear thickening fluid correspondingly the viscosity increases as the shear rate is increased. So, if we try to, let us say, plot the shear stress tau against the shear rate gamma dot, for a Newtonian fluid it will be a straight line. For a shear thinning fluid it will be a curve that looks like this. So, the slope of this curve keeps decreasing as the shear rate increases. So, correspondingly the viscosity keeps on decreasing as the shear rate increases. So, this is the shear thinning behavior, and many polymeric liquids are shown to exhibit this kind of a behavior. So, if we now try and plot the change in viscosity with shear rate. Okay. So, here we have plotted change in the shear stress with shear rate, and this straight line is Newtonian. So, if you plot the change in viscosity or the apparent viscosity with shear rate, this apparent viscosity, then for Newtonian fluid this viscosity will be a constant. So, we will get a horizontal line, but for a shear thinning fluid like a typical polymeric fluid, let us say, initially we will get a horizontal line at small shear rates, and at higher shear rates it will decrease. At very high shear rates it might also again become horizontal. So, at very low shear rates polymeric liquid can behave kind of like a Newtonian fluid, but as the shear rate is increased and the polymer chains tend to elongate, and that will lead to a shear thinning kind of behavior where the viscosity of the material decreases, and at very high shear rates where almost all polymer chains are well aligned in the flow direction, again the viscosity becomes pretty much constant, but the viscosity value will be very low, and that is what is shown by this constant at very high shear rates. The shear thinning kind of behavior of polymeric liquids can be well captured by a model that is called the power law relation, so or power law fluid model. So, here the shear stress tau is related to the shear rate gamma dot by this power law kind of expression, where the m and n are characteristic parameters of this power law equation. So, now the if we try to identify the apparent viscosity in this equation, then the apparent viscosity eta as a function of gamma dot we can just write as m multiplied by gamma dot to the power n minus 1, because if we write apparent viscosity in this way, Then for a power law fluid also we can then write the shear stress as just this apparent viscosity multiplied by the shear rate. Okay. So, apparent viscosity for power law fluid is defined like this, and finally, the viscosity at very small or almost zero shear rates here, that is denoted many times by the symbol eta naught, and that is called the zero shear viscosity. It corresponds to the viscosity of the fluid at almost zero shear rates. So, this power law fluid model is a reasonably good model to describe the shear thinning behavior of many polymeric liquids, and the study of the flow behavior of polymeric liquids is important, particularly in polymer processing operations, where molten polymer is subjected to high shear rates, and the flow behavior can actually affect the quality of product that we get. So, the rheology and the flow behavior of polymer liquids, its study is important from that perspective. Finally, let us look at how the viscosity of these polymeric materials or polymeric liquids changes with temperature, and what is the dependence on the molar mass of polymer as well. Okay. So, if we are talking about a polymeric material and if it is above its glass transition temperature, then the change in viscosity can be related to the glass transition temperature using an equation called the Williams-Landau-Ferry equation, or the WLF equation, and it is typically valid for a temperature range between the glass transition temperature of the polymer and up to 100 degrees above the glass transition temperature. So, the expression for this WLF equation is something like this: log 10 of eta, or the viscosity at any given temperature, by the viscosity at the glass transition temperature, that is equal to this quantity here, where the C1 and C2 are observed to be constants for many polymers, and the universal values of these constants are minus 17.44 and 51.6 Kelvin. Now, this ratio that we have here, this ratio is also referred to as a shift factor AT. So, AT is nothing but the ratio of the, in this case, this particular case is the ratio of the viscosity at temperature T by the ratio of the viscosity of the polymeric material at its glass transition temperature. So, this shift factor AT is actually an important parameter, and this WLF equation that we have written specifically for viscosity, it is a more general kind of equation which appears in the study of what is called time temperature superposition behavior of polymeric materials. So, we will not go into the details of such behavior, but it is important to know that this WLF equation is more general in applicability, and one can specifically apply it to the viscosity change with temperature, but other effects can also be captured using this WLF equation. So, for this viscosity change, the shift factor AT is just the ratio of the viscosities. If the temperature is much higher than the glass transition temperature, so if we are much higher, above more than 100 degrees Celsius above glass transition temperature, then it is proposed that an Arrhenius kind of relationship actually better describes the viscosity change with temperature. So, this Arrhenius relationship is given by relation of this kind, where R is the universal gas constant, EA is some kind of activation energy, eta R is the viscosity at some reference temperature Tr, and eta is the viscosity at temperature T. So, these are some expressions relating viscosity to temperature. We can also discuss the relationship between viscosity and molar mass of polymers, because it is observed that the polymer molar mass actually has a very strong effect on the viscosity of polymers. So, if we are talking polymer melts, then the for low molar mass polymeric materials, where the entanglement of polymer chains is negligible, for such cases the viscosity is seen to be proportional directly to the molar mass itself. Whereas, if the molar mass is crosses above some critical value of molar mass value, the viscosity actually is seen to depend very strongly on molar mass. So, for high molar mass polymers, the viscosity is seen to be proportional to m to the power 3.5 or 3.4, something in that approximate range. So, for this high molar mass polymers where entanglement effects are strong, there the viscosity scales very strongly with the molar mass. Typically, there is some critical molar mass below which entanglement effects are negligible, and we have this kind of relation between eta and m, and above this critical molar mass where entanglement effect of long polymer chains start to dominate, a stronger relationship between the viscosity and molar mass is observed. So, if we plot, let us say, this log of eta versus log of molar mass, then for small molar mass values low slope is observed, and but at higher molar mass values the slope of this curve will be much higher. It will be around 3.4 or 3.5, that will be the slope, and low molar mass will have around a slope of 1, and these slopes correspond to the exponents of this quantity m in these relations. And at some critical molar mass, let us say some m critical molar mass, this transition behavior is observed, and that typically marks the onset of chain entanglement, because the molar mass increase leads to longer chains which have a greater tendency to get entangled. So, with that we will conclude this discussion of polymer viscoelasticity as well as brief discussion of polymer rheology and non-Newtonian flow behavior. And what I will do is leave you with this video, which is a very nice illustration of the interesting effects that can be observed because of the viscoelastic and non-Newtonian nature of polymeric liquids. So, if we look at this video, we have a liquid filled inside a beaker, and a rod is placed inside the liquid, and the rod is being rotated at high speed. So, for a Newtonian liquid, what one would observe is that if the rod is rotated at high speed, then the liquid will typically move towards the periphery of the beaker and rise and get depressed at the center near the rod because of inertial effects. But for polymeric liquids, because of the viscoelastic nature, there are some normal stresses present which lead to rise in the polymeric liquid on the rotating rod that we have. So, this effect is known as the rotating rod or Weissenberg effect, and this particular video, as mentioned, is taken from a source which is the website of Professor Hastropoulos at MIT. So, it very nicely illustrates a very interesting kind of flow behavior of viscoelastic polymeric liquids, where the liquid tends to climb on top of a rotating rod. That will conclude our lecture for today, and hopefully these last couple of lectures have introduced you to the concept of viscoelasticity as well as how it applies to the mechanical response of polymeric materials. In the next lecture, we will look at another interesting kind of mechanical behavior of polymers, in particular that of rubbery cross-linked polymers, and that behavior is what is called rubber elasticity. Thank you.